Welcome to section 1.5. In this section, we're going to be talking about the concept of continuity for functions. So we have already explored the concept of limits. We have seen how we can deal with limits as x approaches certain values, as x is approaching infinity. We've looked at some of those behaviors. Now we're going to talk about what it means for a function to be continuous. So if f of x is a function, we say that it is continuous at the value x equals a if the following conditions are all true. So first, the function at a, f of a, must exist. Okay, so the function has to have a point there. It must exist there in order to be continuous. The limit of the function as x approaches a must exist. Okay, so the limit has to exist coming at it from both sides. And those two values that we got in part 1 and part 2 must be equal to each other. Okay, so the function exists, the limit exists, and those two values are equal. Technically speaking, this third one encompasses both of these because if they're going to be equal, they both have to exist for that to be true. But we go ahead and state it as 3 conditions just so that we can keep that perfectly clear. Now, when we're talking about continuity as a concept, we like to visualize it graphically. So like if I had a curve, from like point A to point B, and the curve looks something like that, this would look continuous, right? It has no like holes, no gaps, no breaks in the graphs, whereas something like, like this would not be continuous because there's this big gap. Or you could have, something with like a hole in it there. Or you could have something, like an asymptote that goes up and down like this. Just anywhere that you would have to, as you're tracing the curve, if you would have to like pick up your pencil and move it and then put it back down to continue the curve, that would be discontinuous, okay, or not continuous. So let's take a look at some examples here. So observe the continuity of the following functions. So the first thing we want to look at is for this rational function, are there any points where this function does not exist, right? Are there any x values that do not produce an f of a, like we talked about in the first part here? And the answer, of course, is yes. There is one value that gives us a problem. Okay, because in the denominator, you cannot have a 0. So x minus 2 cannot be equal to 0, which means that x cannot be equal to 2. Okay, so x equals 2 does not produce a real value out of this function. So there is no point there. Okay, there is no output there. So we say that this function is discontinuous. That just means not continuous at x equals 2 because f of 2 does not exist, or DNE for does not exist. And if we were to graph this, this actually does produce a function that is linear in nature. So our gap would be somewhere right around here. And the graph is going to go kind of like that. Just pretend that that's that's straight. Something like that. So this is roughly what this graph looks like. And again, if you're talking about it graphically, like if I'm drawing the curve, I have to stop and pick up my pencil to move it over this gap, this hole in the graph, and then keep on going. So we have a discontinuity at this point at x equals 2. Now, if we look at part B for g of x, notice that this is a piecewise function. Okay, so we have this function if x is not 2, this function if x is 2. But notice the first function up here is the same as part A, right? It is the same function. What we're trying to do here is we're saying, okay, I know that this original function doesn't exist when x is 2. So what if we just take that function for everything except x equals 2? And then we basically try to plug the hole. I say when x is 2, I'm going to make the value 1. And we're going to see if that works. So this time, so we know g of 2 is 1. And again, that's because we're saying if x equals 2, then g is 1. So we know that the function exists there. The next question, what about the limit as x approaches 2 of g of x? So we take limit, and because we are approaching 2, we're not at 2, we're going to use this function. Okay, so we're going to use the one for x not equal to 2. And we can work a little factoring magic with this numerator. It gives us x plus 1 and x minus 2 over x minus 2. Those quantities cancel. So we have limit as x approaches 2 of x plus 1, which is 3. So if we look at our conditions, condition 1, the function has to exist. It does. Condition 2, the limit has to exist. It does. All right, so this is 1 and 2. Condition 3, the value of the limit must be equal to the value of the function at that point. And so the million-dollar question, is 3 equal to 1? Of course not. So it turns out in this case, what's happening is we tried to plug the hole, but when we put the point in, we put it right here. So now our function is going. It stops, it jumps down here, and then it jumps back up and continues going. So this function is also discontinuous at x equals 2. Now that we've seen all of these pieces together, we can look at part C, so h of x, which is, again, a piecewise function with the same formula when x is not 2, but this time when x is 2, we let the output be 3, because that's the value that we got for the limit back here. So for this one, if I graph it, gap right there, but the 0.23 is on the graph. So this time it plugs the hole, and we can just go straight across, and we have continuity. Okay, so we can see in this case, h of 2 is 3, and that is the value of the limit as x approaches 2 of g of x. So this function is continuous at x equals 2. Okay, so we need the function to exist there. We need the limit to exist approaching there. And then we need those two values to be equal to each other. That's how we're going to get the continuity that we're looking for. Now, if we're trying to determine whether a function is continuous over an entire interval of points, we don't want to have to check point by point, right? We would be doing that literally forever to do this test over and over and over again for every single point on an interval. We will be working with primarily polynomials and rational functions at this level. So it's important to note here that both these types of functions, polynomials and rational functions, are continuous at every point in their domain. So in order to determine continuity, this is something we could prove if we were going a little bit deeper into the kind of the heavy calculus topics. You could prove that polynomials and rational functions are continuous at every point in their domain. Polynomials, because their domain is all real numbers, polynomials are continuous everywhere. Rational functions are continuous everywhere except for the points like these, where you have the hole in the graph because the domain is restricted. Okay, so this is a rational function we did an example with. But this is going to be very helpful for us to determine continuity more quickly just by recognizing the functions. So let's take a look at a couple examples down here. So we have f of x. We're trying to determine the interval of continuity for the following piecewise functions. So we have a piecewise function with this formula when x is less than or equal to 4, and this formula when x is greater than 4. This formula here is a linear function, and this is continuous because it's a polynomial. And this one is also a linear function. So this one is also continuous, and also because it's a polynomial. Now the question that we have to ask, because we're using this function for everything less than or equal to 4, this one for everything greater than 4, they're continuous on their separate parts, but do they meet in the middle? Right? Because you could have a perfectly continuous line over here, a perfectly continuous line over here, but if they don't match at this meeting value of 4, then the curve will still be discontinuous there. So we need to check at x equals 4. Okay, so we'll go ahead and get f of 4. We get, it's included on the first function, right? That's the or equal to sign right there. So we get 1/2 times 4 minus 3, so that's negative 1. If we check the limit as x approaches 4 from the left, we are on the left-hand line, which is basically just the calculation we just completed. If we check the limit from the right-hand side, we're on the negative x plus 3. So plug in 4 again, and we also get negative 1. If the limit coming from the left and the limit coming from the right are the same, that means that the entire limit is that value, okay, or the two-sided limit of f of x is negative 1. So we got the function value is negative 1, and the limit is negative 1. These values, of course, match. So limit as x approaches 4 of f of x equals f of 4. So it is continuous at x equals 4. Now it's asking about the interval where it's continuous. We know it's continuous for everything less than 4. We know it's continuous for everything greater than 4. And now we know it's also continuous at 4. And that's everything, right? Everything less than, greater than, and equal to. So it is continuous on the interval negative infinity to infinity. Okay, are all real numbers. Let's try another example, pretty similar in style, and we still are using 4 as kind of the splitting point here. So we have a similar situation, similar situation, two linear functions that are going to be continuous on their separate pieces of the domain. But the question becomes, what about at 4? Okay, just like the last one. So if we take limit as x approaches 4 from the left, plug in 4, that's negative 2 plus 4 is 2. So limit as x approaches 4 from the right, we take 3x minus 9. 12 minus 9 is 3. So coming from the left, this function is headed to 2. But coming from the right, the function is headed to 3. So we have something, looks kind of like this. It's heading to 2, and then it's heading to 3, like that. And there's going to be a gap there. So the limit as x approaches 4 of f of x, that two-sided limit, that complete limit, does not exist because we're approaching two different values from two different sides. So we know that it's continuous on the separate pieces, but in this case, they didn't meet at 4. They didn't match up. So we have to exclude that from our interval. So it'll be everything but 4. So negative infinity to 4 with 4 to infinity. So that will be our interval of continuity. And then if we look at part C, the last one down here, we see, again, two linear functions. And you could go ahead and check both of them to see where they meet up at 4 if you wanted to. But what I want to look at is something in the problem here. This function has the formula 2x minus 1 for x less than 4. It has the formula 1/4 x plus 5 for x greater than 4. But notice there is no equal to here, right? There is no value stated for the function when x is equal to 4, which means that it doesn't even really matter where the function is headed as we go to 4, right? The limit from both sides doesn't really matter because we already know f of 4 does not exist in this case. So it will be discontinuous at x equals 4. So we'll get the same interval that we had in part B. And that would be all real numbers except for 4. All right, so that brings us to the end of section 1.5 in our discussion on continuity. When we come back in 1.6, we're going to be finishing out the chapter and looking at kind of bridging the gap between algebra and calculus when we talk about average and instantaneous rates of change. So I will talk to you all in the next one.